Section 2.4 is going to discuss scatter plots and correlations. Specifically, that's going to be linear correlations. So let's take a look at some data that I happen to get from the National Oceanic and Atmospheric Administration. Here's the actual data itself. The number here on the left in the X column is the year. Starting with the year 1900 is year 0, so 1910, 20, all the way up into the year 2010. And in the right column here, the Y column, is the average temperature here in Oakland County. So we're not looking at the whole world, we're just looking what's been happening to our weather here in Oakland County. So it's a huge data set, and I've boiled it down to average by decade. And even though this doesn't start at 0, you can still look at this and see, see what you see. When you look at this data set, this graphed over time, what's striking to you? Is there anything interesting or noteworthy? Nick?
The rise and the dip.
All right, rise and then a dip. And then a steady rise again. Is there an overall statement we can make out of this? Logan? Yeah, looks like there's some kind of a linear trend here, right? Looks like the temperature is increasing. At the turn of the last century, or the turn of the 19th century into the 20th, the average temperature in Oakland County was around 45 degrees. Now it's close to 49 degrees. Okay, and that's like 8 years old too. So 7 or 8 years old. My guess is going to continue. So what we're looking at is there some kind of a correlation? Now later on, we'll be able to quantify that correlation and start coming up with a regression line. I'm not worried about the regression line just yet, but what I would like you to be able to do from this section is get scatter plots like this, and also understand a little bit about correlation, the linear correlation coefficient. And that was the purpose of your handout. So if you don't have a handout, I think got a couple extra up here. So come help yourself. We're going to talk first of all about linear correlations and the linear correlation coefficient. So we use the letter R to denote that, the linear correlation coefficient. Big fancy word, but really it just represents the strength of a linear relationship. How good, either in a positive or negative sense, is your linear relationship. Now the value of R can go between 1 and -1. So let's write that down for ourselves here. -1 is less than or equal to R is less than or equal to 1. Now the extreme values are perfect linear relationships. So let's see a couple examples of some perfect linear relationships. So here's 2 on this handout. This is a perfect negative linear relationship. This is a perfect positive linear relationship. The negative and positive simply reflects the slope of the line represented by your data. If as you move left to right, your line is decreasing, it has a negative slope. So that perfect negative correlation would be -1. If as you move from left to right, your line is an increasing line, has an increasing slope, then this is going to be a positive linear relationship. And here this is a perfect positive relationship, so you have a correlation coefficient of 1. Now that's your linear correlation. These are perfect linear correlations. You're not often going to get such perfect linear correlations. Okay? What if it's not perfect? Well, the farther away it is from perfect, the farther away it's going to move from these perfect linear correlations. So if you move over here, is there still some kind of a linear trend represented by our data? What do you think? Yeah, it still looks pretty good. Is it perfect? No. But that's why it's not exactly a -1. It's close to -1, but it's not exactly -1. There's still value here. In knowing what the value of x is, I have a pretty good idea, not perfect, but a pretty good idea what the value of y is going to be. So, it helps out. How about over here? Does knowing what the value of x is help you make a prediction as to what the value of y is? If I told you what x is over here, or over here, you have a pretty good idea what y is. But if I told you the value of x here, well, it could be this one, this one, this one. Just don't know. It's kind of a blob. So this is getting close to 0. All right. 0 means there's no correlation. There's no linear correlation. So that's not very helpful. On the positive side of things, perfect linear correlation. Still not bad. Over here, R value of 0.86. I think lots of researchers in the social sciences would be thrilled to get a R value that big. But what about this last one here? Is there a nice relationship between x and y here? Yeah, there's definitely a relationship, right? But is it a linear relationship? Can it be represented with a line, just one line? No. And because of that, you've got an R value of 0. So those are some of the extreme values that you can get. You can get things that are close to -1 or close to +1, your perfect linear relationships, and then things that are different than that, but maybe close to it. And finally, something near 0 is saying there's just not much of a linear relationship between these two things at all. One of the linear relationships that I'm sure is a hot button for a lot of people right now is a relationship between some data that you can come up with from various models and the height of a storm surge. Right now, Florida is experiencing a huge hurricane, or I guess it's just passed. But of interest to a lot of people is, well, how big of a storm surge is there going to be? How high is the water going to rise above its usual levels? And you can predict this stuff. There's a nice relationship between a bunch of different variables that are pulled all together to get this composite value, and then you predict how high the storm surge is going to be. How high, where should you put, the safe havens? Are you far enough inland? Or is your storm surge going to hit you? So definitely is something worth knowing. Okay. So with our kind of basic understanding of R, let's discuss one of the problems in the book. And it's just really asking you, do you understand some of these extreme values and what kind of data might represent these extreme values? So we'll start with problem number 4. So the goal here for us is to try and decide, if the value of R, our linear correlation coefficient, in this problem is going to be close to 1, -1, or 0. That's what I see this problem as. The first part of it, part A, says you've got two different data sets. That is height in inches and height in centimeters. So are those two pieces of data going to be linearly related? Is there going to be some nice relationship between your x's and y's if I graphed them? Good. So is it going to be 1, -1, or 0? What would you guys suspect? 1. Should be 1 because there's an exact linear relationship, and that is think each inch is worth 2.54 centimeters. So, or y equals 2.54x. So it's just going to be a perfect straight line. In that case, you're going to get a nice linear correlation of 1. Good. Let's move down to part B here. IQ scores and measured height. So if you took somebody and measured their IQ score and also their height, is there going to be some kind of relationship between those? No? Wait, smarter people aren't taller? Come on. That'd be great. I mean, I'm 6'1", so it'd be fun. All right. No, it's not a measure of your intellect as to how tall you are. There's no correlation, or at least I'd be really shocked if there was some kind of a correlation here. There's not. How about the last two? What I want you to do is discuss these with a neighbor and come up with your own. 0, 1, or -1 for the last two. So turn to a neighbor, please, and chat about that. Go ahead, feel free. Pause. It's my manual pause. Don't have a pause button. Sorry. The IT department won't spend the $800 to give me a pause button. Still paused. Okay, Kayla, what do you think? Pulse rates and measure IQ scores. People with a higher pulse rate smarter or lower pulse rate smarter? No? Pretty random? So what do you think the value of R would be for a data set like this? Yeah, it'd be somewhere around 0, close to 0, right? Now when you have computers, they can still calculate these numbers, but it's not really going to be meaningfully different than 0. All right, thank you. Nick, how about the last one? Heights measured in centimeters and those same heights listed again, but with negative signs. Heights, yeah, -1, a perfect linear correlation. If you're just flipping the sign, there's still going to be an exact relationship, but it's going to be negative. So, yeah, the answers would be 0 and -1 for the last two. Are you okay with this? You're starting to get a semblance of what that R value represents? Because that's the big thing here. Yes?
They're trending in the opposite direction. Does that mean they're negative in a sense?
Yes. So, I'm trying to think of a negatively sloped relationship here. Let's see. Is there one in the book? Let's see. What would be an example of a negative slope? I can think of positive ones, but where's a negative one? Something that goes up and something else goes down. Here's one. How about supply and demand? If supply goes up, or if demand, let's see, if the supply goes up, the price will go down, right? So that would be a negative slope. So, okay, good question. Let's actually practice calculating one of these things. So let's see if we can't plug in some data and calculate it. Now, I know I asked you to open up a Google Sheet. We're going to use that data later. Right now, what I'd like us to do for our Google Sheet, let's just get rid of this. Delete chart. We're going to enter the following data sets. So this is for problem number 6. And it represents the measurements taken from wild bears. The whole data set's found in Appendix B. We're just going to look at a little subset of this. So they measure the chest, and I'm assuming that this is the circumference of the chest in inches, and then the weight of the bear in pounds. We want to see, is there going to be some kind of a linear relationship between these two? So if you would copy this data into a Google spreadsheet, that'd be great. In fact, once you copy it, highlight your data. Now it's helpful if you put in the first row the name of your columns. So Let's see, maybe we can make this a little bit bigger. No, I don't want to do that. I was hoping I could zoom in here. Got it. All right. So the chest measurements going down are 26, 45, 54, 49, 35, 41, and 41. The weights in the next column are 80, 344, 416, 348, 166, 220, and 262. By the way, you can see from this data set we're not going to get a perfect value for R. You could not get R equals 1. Can anyone spot why? How come you're not going to get a line that goes perfectly through our data? These last two, go ahead. Exactly. You're not going to get a line other than a vertical line that goes through these 2 points. It can't. You have 2 different y values for the same value of x. So whatever our value of r is, and we're not going to worry about computing it now, our value of r is not going to be 1. Highlight this data, and then click to insert a chart. Now, I can do it from the insert chart menu. Some of you might have a laptop that's wide enough that you'll see that insert chart here. I think if I go over more, I can find it there. We want to insert a chart. The nice thing about highlighting your data ahead of time is that Google kind of suggests something for you. In this case, no, that's not right. This suggested a column chart. I don't want that. I was expecting it to. You disappoint me, Google. Sorry. We'll go down to scatter because we want a scatter chart. There we go. What do you think? Is there some kind of a linear trend here? Roughly speaking, throw out a number. What would be the value of R here? What would you guess? Yeah, 0.9 sounds good. It's going to be something close to 1. It's not going to be perfect, but yeah, around 0.9. So knowing the size of the chest of this animal helps you determine the weight. So if you know one, then you certainly know something about the other. So there's a correlation here. And that's what we're trying to determine in this section is, what kind of a correlation is there between these 2 variables. Now, as a reminder, correlation doesn't necessarily imply causation. And we've talked about this before. One of the examples that I gave saying that correlation and causation are different would be number of hours of TV that you watch on the x-axis and your weight on the y-axis. All right. Watching more TV doesn't cause you to be overweight, but there is a correlation there. There's a tendency that way. Okay, how are we looking on correlations here? So far, so good. I'm not going to be asking that much of you in terms of the homework. You might want to look over problems like number 4 again in advance of the exam. But for homework, try problems 1 through 7. That's just the odds. Sorry, I know that sounds like a lot, but I'll give you 2 days to work on it, all right? 1 through 7 odds in the homework. Yes? There is no similar set of homework for the 12th edition. He totally rewrote this section, so there's nothing analogous there. But if you look at the video, I'm sure that you can figure out the homework from the video. Okay? All right. Any other questions regarding section 2.4? Okay. Oops. My bad. All right.